Hello and welcome to another edition of TutorTube, where the Learning Center's lead tutors help you understand challenging course concepts with easy to understand videos. My name's Evie, lead tutor for math and political science, and in today's video, we will explore further applications of derivatives. Let's get started. Let's begin with some more challenging derivatives. For number 1, we will take the derivative of the cube root of 1 plus cotangent squared x. To do this, we will change it into a power, and then we will apply the chain rule. The chain rule says that we need to multiply times the derivative of the outer by the inner. So the derivative of the outer is the cubed part, which we took the derivative of on the left side, and then we need to multiply times 1 plus cotangent squared, which is the derivative of the inner. Now we simplify this by doing chain rule again, because the 1 plus cotangent squared involves chain rule because of the cotangent. Cotangent's derivative is negative cosecant squared, so we multiply everything by that. And then we simplify it. And from here we will use the laws of algebra that say that we can put a negative exponent on the denominator if it's on the numerator. And then we will simplify by putting it back into a root format. For number 2, we want to take the derivative of this function. To make it a little easier, we will let a be sine cubed of 2x, so that the derivative is just cosine of a to the power of 4. We apply chain rule in this one again. Remember, we need to multiply times the derivative of the inner, which is cosine of a in this case. And then cosine of a's derivative is negative sine a times a prime because of chain rule. Let's substitute a back into sine cubed. And then we see that we need to take the derivative of the last sine cubed all the way to the right. So we'll do that, and we get 3 sine squared times cosine 2x times 2 because of the argument of 2x. Now we'll clean this up, and how we'll do it is we'll multiply the 4 on the outside times the negative 1 times the 3 times the 2 all the way at the end. That is negative 24, which will go all the way in the front. And then we'll write the cosines first and then the sines next. So negative 24 is a number which goes out in front, and then cosine cubed, cosine, sine squared, and then sine. Let's continue with some more challenging derivatives. The first example, we're taking the derivative of this function. To do this, we need to find a way to get the x out of the exponent, because we can't take the derivative if the x is in the exponent the same way that we normally do. To do that, we will take the natural log of both sides. We do this because log rules allows us to do some simplification steps. The first step we can do is splitting up the log on the right side because it's being multiplied inside of the log. So we split it up into addition. And then the second part of that log, we use the log rule where we can bring down the exponent. So now we have the x out of the exponent, and we can distribute that x with the ln of 4. And this is what we get after we distribute the exponent. Now we're ready to take the derivative, so we will use implicit differentiation to take the derivative of both sides. Remember, on the left side, the derivative of ln is always 1 over whatever's on the inside of ln times its derivative. So we have 1 over y times y prime. Y prime is what we're solving for. On the right side, the derivative of every single thing that has an ln and just the ln is 0. So ln of 3 is 0, and 5 ln of 4 is 0. 7x squared ln of 4, that is 14x ln of 4. Now we solve for y prime by multiplying both sides by y. Then we go all the way back and remember that we have y, so we substitute that. Now we just have to clean this up a little bit. So remember, we can't do anything with the ln of 4 because the 4 is on the inside of the log, but we can simplify the 14x with the 3. That will be 42x. And then we'll rearrange it neatly, just like this. Number 2, similar that we have to do algebra before calculus, so we will do some simplifying steps. The first step is to change the exponent into a fractional exponent. And then we'll use the log rule to bring down the exponent. And then in this case, the log is being divided on the inside. So that means splitting up into subtraction instead of addition in the previous problem. So the 1/3 actually gets distributed to both things. Now we're ready to take the derivative. We use chain rule again. So ln 1 over the inside times the derivative of the inside for both things. That's what we get. Then we can factor out that 1/3, and on the inside of that we have to simplify this by getting common denominators, multiply the denominators, and make sure that you distribute the top. Distributing the top will give you this, and then you will simplify that, and the top is not factorable, so we'll leave it like that, and the bottom we will bring in the 1/3. Let's take a look now at some application questions. The first is, what is the average rate of change of the function from 0 to 5? To answer these kind of questions, all you need to do is remember this formula. This formula represents the distance you went minus the distance you started at, divided by how long it took you. So we plug in 5, and we plug in 0, and we subtract the 2. And then we divide it by how long it took us, which is 5 seconds. Plugging that into the formula, we get this, and that's about 0.463. For number 2, we have the function that represents the object's position based on the time. We want to find the velocity between 0 and 3 seconds. The velocity is actually the application of average rate of change, so we use the formula that we talked about earlier to solve that. For number 2, that's finding the instantaneous velocity. So that is actually taking the derivative of the function, because that will give us the velocity at any instant, any time, x. Then we want to know at what particular time does the object have no movement. That is when there's 0 velocity. So if we have the instantaneous velocity and set it equal to 0, solving that would give us 7.5 seconds. Let's now take a look at some related rates problems. We have a video dedicated to related rates, but we weren't able to cover every single topic that you may see. So here are 2 more examples. The first is a kite 50 meters above the ground. It's moving at a horizontal rate of 3 meters a second. We want to know what the rate at which the angle between the string and the horizontal is decreasing at when 150 meters of that string has been let out. To solve this, we need theta prime. To get theta prime, let's first create a relationship for theta. Since we have the opposite and the hypotenuse, that relationship would be sine. Take the sine inverse and we get theta. Now we need to create a relationship that has theta and x prime in it. X prime is at 3 meters a second. Take the derivative of this and we'll have that relationship. Plug in theta and plug in x prime, which we solved for and which was given. Then remember, cosecant squared can be rewritten as 1 over sine squared. Then you can multiply both sides by sine squared. And when you're plugging this in the calculator, remember to be in radians. Then you'll get this. A street light mounted at the top of a 20-foot pole, and a 6-foot man who walks away from that pole at a rate of 8 feet per second. Given that, we want to know how fast is the tip of the shadow moving when that man is 30 feet from the pole. This is a diagram that will depict that information. To solve it, we'll use properties of similar triangles, where the bigger triangle represents the tip of the shadow, a plus b, and the smaller triangle represents the shadow, but not the full distance, and the man's height. We'll use these 2 triangles to create a relationship where we'll solve for one of the variables, b. We solve for b because we need to get what we're concerned about, the bigger triangle, we need to get that into one variable. So we'll plug in b for a, and this represents the tip of the shadow, remember. And we'll get the representation of that distance. Since we want to know how fast the tip of the shadow is moving, we take the derivative of our expression. A prime is the distance of which is changing. So the distance that's changing is 8 feet per second. The man is moving at a rate of 8 feet per second, so his distance is changing by that much. So we plug in 8 for A prime. Since we didn't have A, we don't plug in 30. We just plug in the A prime, which is 8. And we get 11.43 feet per second. Let's practice mean value theorem. For mean value theorem, if we have differentiability on a specified interval and it's continuous on a specified interval as well, we can say that there exists at least one point on the graph called C where the tangent line of that point and the secant line of the entire interval are equal to each other. We express this with a quote-unquote mean value theorem formula to solve different kind of problems. Let's look at the first problem. Find all possible C in the specified interval satisfying the conclusion of MVT. This function is differentiable and it's continuous, so we can use the MVT formula. The MVT formula is specified as this. If we take the derivative of the function we're given and plug in C as the point, and we set that equal to the average rate of change, we can solve for C and get our answer. Now, we need to take the derivative of the function. In this case, this involves product rule. Now we need to plug the values into the average rate of change, and we'll get 4. Then we need to set those things to equal to each other, and if we subtract 4 and get common denominators, this is what we'll get. Then if we simplify and set the numerator equal to 0, since the denominator can never be 0, we can move over the 4 and square both sides. And then we'll be left with this, which will distribute the 16, and then combine like terms to set everything equal to 0. Now we can use the quadratic formula, and we'll have the two C values that correspond with the MVT formula. Now, for the second example, we have f of 1 being 10 and the derivative being at least 2 within the specified interval 1 to 4. How small can f of 4 possibly be? Well, if we use the MVT formula, then we'll have this expression. And we're just wanting to find f of 4, so we solve for that, multiply both sides by 3 and add 10, and f of 4 should be at least 16. Let's now examine some common business examples. In this case, we have a total cost function, and we want to figure out what the expected cost to produce the 10th item is. Then we want to figure out the actual cost of producing the 10th item. For the expected cost, we need to find the derivative. Once we find the derivative, we can plug in 10, and that will give us the cost to produce the 10th item from the 9th. To get the actual cost to produce the 10th item from the 9th, we need to get the cost of producing 10 total items, get the cost of producing 9 total items, and subtract the 2. So plug in 10, plug in 9, and then subtract. Once you do that, you get $170.50. So we can see that the expected cost that we calculated using the derivative is very, very close to the actual cost of producing the 10th item. The second question is, we have a function, and it represents the total number of electric vehicles t years from now, in millions. We want to estimate the amount by which the number of vehicles will increase from now to the next 6 years. How we do that is by taking the derivative. In this case, we'll express the derivative as dy, the change in the number of vehicles, over dt, the change in time. That is going to be the derivative of the function. So if we solve for dy, the change in number of vehicles, we'll get this. Now, remember that t is from now, so that's essentially 0. 0 years have passed. And the change in years is 6. So from 0 to 6 is what we're concerned about. Therefore, we plug in 0 for t and 6 for dt, and we'll get about 18 million vehicles that's expected in the next 6 years. Thanks for watching another edition of TutorTube. I really hope this video helped. Please subscribe to our channel for more exciting videos and check out the links in the description below for more information about the LC, and follow us on social media. See you next time.